All right, welcome. Let's chat through and discuss the section 7.3 trig substitution exercises. Not working out, but let's just talk through it. So right, in this first example, we've got a classic form, number plus variable squared. That mimics the trig identity 1 plus tan squared. So in fact, here we would want x equal to tan theta. That would do it. And yeah, once you let x equal to tan theta, you're also going to want to compute what dx is. Dx would be what? Just secant squared theta d theta. So then you're going to plug tan theta in. So you'll get what? Tan to the fifth upstairs. 1 plus x squared, 1 plus tan squared is just secant squared. The square root of secant squared is just secant. And then you'll have the secant squared theta d theta. One of the secants upstairs cancels with the secant that appears downstairs. And I think you'll end up with tan to the fifth secant. So in that case, what will let u equal secant and view that as a trig integral. So that'll be a nice one there. Who knows when it turns out? Oh, they're not even asking you to evaluate. They just want it in terms of theta. Oh gosh. So then all you got to do here is just do tan to the fifth over square root 1 plus tan squared, and then do the secant squared. The most important thing here is to make sure that dx is not just d theta. Dx is secant squared theta d theta. Okay, what about this next example? Hey, we got 49 minus x squared, number minus variable squared. That mimics the form of 1 minus sine squared. 1 minus sine squared, well, you'd almost want x to be sine theta, but that's not enough here, right? Because we want the x squared to also equate the coefficients. So we'd want x to be 7 sine theta. That way, whenever we would square 7 sine theta, we get 49 sine squared. The 49 factor out, and you'd have 1 minus sine squared equal to cosine squared to simplify out. And so, yeah, again, we're just transforming. We're not actually evaluating, which is nice. That's a simpler step. We're just utilizing the evaluation procedure. Upstairs, we have 7 cubed sine cubed, so be it. Downstairs, we'd have square root 49 minus 49 sine squared. And then dx, don't forget dx. Differentiate both sides of your substitution. You would have dx equals 7 cos theta d theta. The d theta is already there, so we just have to make sure the 7 cos theta is hanging out within our expression. Right, similar story here. But in this case, we have x squared minus 3. Okay, now x squared minus 3, variable squared minus 3, that mimics the trig identity secant squared minus 1. In order to equate coefficients, we're going to need the x to be square root 3 secant. Square root 3 secant would do it. So, oh boy, that looks like a funky notation, but whatever. Square root 3 secant theta is the way to go, because whenever you plug that in and you square, you'll get 3 secant squared minus 3. Factor the 3 out, you have secant squared minus 1, which is simply tangent squared, and then you can sort of simplify the square root. We don't have to do any of that business here because we're not evaluating the integral, but so be it. Upstairs, we would have 3 secant squared. Downstairs, we'd have 3 secant squared minus 3 inside a square root. Don't forget the dx. Differentiate both sides of x equals square root 3 secant theta. You get dx equals square root 3 secant theta tangent theta, because derivative of secant is secant tangent. And yep, the d theta is already in there, so that would be good to go. Right, what about this case? Oh, they're already telling you to use x equals 5 tan theta. Of course, we know that because an identity with number plus x squared would mimic the form of number plus tan squared. Number plus tan squared equals secant squared. Right, the triangle that gets labeled here, if you just divide both sides by 5, I think that's the easiest way to see it, then you'd have tan theta is x over 5, tan theta x over 5, opposite over adjacent, opposite x adjacent 5. It looks like this guy is our guy. The remaining side is always going to be the square root upon which you build all of your logic. That is not coincidental. It happens every time. What about the next one? Okay, so this one's a little bit more sensitive because we've got the 4x squared minus 25 inside the square root. That's like a slightly unconventional form. One way to see this is you could factor out a square root 4 from this. If you factor out a square root 4 from this, you'd have x squared minus 25 over 4. 25 over 4 has a square root of 5 over 2, and that's why we would use 5 over 2 secant in this case. Why secant? Because when you have variable squared minus a number, that takes the form of a secant squared minus 1 trig identity, right? Because secant squared minus 1 is just tangent squared. And that's the idea. But assuming that x is 5/2 secant, push the 5/2 to the other side, multiply both sides by 2/5. You'd get 2x over 5 equals secant. Remember, secant is the reciprocal of cosine. And so, right, the 2x that would be upstairs when you multiply both sides by 2/5, The 2x upstairs would be the hypotenuse, the 5 would be the adjacent. So I'm looking at choice A here, and the square root that pops out via Pythagorean theorem is in fact the exact square root we built our logic off. Again, not coincidental. To evaluate the integral completely, right, you got to do what you would have done in the previous exercises where you're not only plugging in x, but you're also plugging in dx by differentiating this. Differentiating, you get what, 5/2 secant theta tan theta d theta. It's going to look like a lot at first, but you let the square root simplify, cancel out everything else, and you'll get down to a digestible form. So you got to sort of trust in the process here, and good things will happen. Right, what about this example? Hey, we got a definite integral here, so be it. We'll deal with this as we get to it. In fact, they're already suggesting to transform the bounds from t to theta. I think that is advantageous here, right? Because when you undergo a trig substitution, you're going to convert the whole integral in terms of theta. Why have to go all the way back to t with your antiderivative? In fact, you could bypass your triangle here by just evaluating with respect to theta. So of course, t is 5 tan theta here. I say of course because when you have an identity of the form number plus variable squared, that's of the form essentially 1 plus tan squared, or sort of itching to be of the form 1 plus tan squared. In this case, to equate coefficients, we would need t not to just be tangent, but t to be 5 tangent. This way we'll get 25 times quantity 1 plus tan squared within the square root, which would simplify to be what, just 5 secant downstairs. Don't forget the dt upstairs, so that's going to be 5 secant squared upstairs. But now whenever you get that entire integral in terms of theta, why not just convert the bounds to be in terms of theta as well? So t equals 0. You have 0 equals 5 tan theta. In other words, tan theta would have to be 0, and the only angle for which tan theta is 0 is going to be 0, so you'd have a 0 downstairs as well. And then if you had a 5 on the other side, you'd have 5 equals 5 tan theta, so you need to find the theta where tan is 1. But tan is 1 at what, a 45-degree angle, so pi over 4. So now the new upper bound becomes pi over 4. And if you check it out, whenever you evaluate this integral with respect to theta, because you've got the definite integral here, you could bypass the triangle altogether. You essentially already leveraged the triangle by converting your bounds from t to theta, and the evaluation is not too terrible. Another definite integral. How about that? We get to avoid a triangle one more time. In this case, they're suggesting the substitution of 3 over 4 sine theta. Even if you didn't have that suggested, the way that you could get that is by essentially factoring out a square root 16 or factoring out a 4 from the denominator. If you factored out a square root 16 from the denominator, you'd have 9 over 16 as this first term, but 9 over 16 minus x squared uses a sign identity because that mimics the form of 1 minus sine squared. But what would the x have to be in order so that it's squared to have a coefficient of 9/16? Well, the x would have to be have a 3/4 in front of it. So 3/4 sine theta is the appropriate substitution indeed. To compute dx, of course, you just differentiate both sides. So we'd have 3/4 cosine theta d theta here. The d theta is already expressed. And then since we're doing a definite integral, we can actually avoid the triangle consideration if we just convert everything in terms of theta. So letting x equal 0, sine theta would have to be 0. That occurs at theta equals 0. And letting x equal 3/4, 3/4 equals 3/4 times sine theta would require sine theta to be 1. But sine theta is 1 precisely, wait, sine theta is 1? Oh, yeah, of course. That's at the top of the unit circle at theta equals pi over 2. So pi over 2 is going to be the top bound there. And so converting to theta, you go between 0 and pi over 2. Now, whenever you integrate this thing, you're going to get some expression in terms of theta. Rather than having to use the triangle to go all the way back to an antiderivative function in terms of x, why not just use the antiderivative function in terms of theta and use your converted bounds between 0 and pi over 2? That would be simpler, right? That's a savings for sure. Okay, this one here. Okay, now we're doing like the full rendition. This is about as full throttle as it gets here. Let's see, x squared minus 36. So that's taking the form of variable squared minus a number. I'm thinking of the identity secant squared minus 1 here. So we're going to want x to be in terms of secant, but not just secant theta, but rather 6 secant theta, so we can equate coefficients. Letting x be 6 secant theta, the dx here is going to be 6 secant theta tan theta, because what, the derivative of secant is secant tangent. And so there's going to be a lot of trig functions going on, but once we put all the trig functions in there, the resulting integral should be no more complicated than anything we saw in last section's exercises. So we worked through the integral in terms of theta, and yes, When we get to the final step, because we utilize the substitution x equals 6 secant theta, divide both sides by 6, you'll have x over 6 is secant. That would mean x over 6 secant, secant is hypotenuse over adjacent. The x would have to be the hypotenuse, the 6 would have to be the adjacent, the missing side will be the square root x squared minus 36, and then you could compute within the triangle to deduce what the other trig functions would evaluate to for that given theta. Last one here at the bottom, we got x squared minus 3. Hey, this is also a secant integral, as it turns out. And in this case, we need x equals square root 3 secant theta. Letting x equal square root 3 secant theta, then when you square, you get 3 secant theta. The 3's would cancel, factor out, excuse me. And then you'd end up with what secant squared minus 1. Secant squared minus 1 is tangent squared. And 3 tan squared would simplify by the square root to just be the square root of 3 tan theta downstairs. What about the dx? Well, if x was 3 secant theta, the dx would be, or excuse me, square root 3 secant theta. The dx would be square root 3 secant theta tangent theta d theta. It's a lot of symbols, right? But if we trust in the process, the resulting integral in terms of theta will just be a trig integral, no worse than what we saw in last section. And then as a result, we can process further from there. When we get down to the resulting antiderivative in terms of theta, remember to use a triangle here. In this case, we had x equals square root 3 secant theta. So using x equals square root 3 secant theta and dividing that square root 3 to the other side, we would have a ratio of x over square root 3 equal to secant theta. But secant is always hypotenuse over adjacent. So x over square root 3, hypotenuse over adjacent, hypotenuse x, adjacent side square root 3, opposite side turns out to be square root of x squared minus 3. And then life is good. We can evaluate all of our trig functions because we have a right triangle using SOHCAHTOA. Life will be good. So, hey, that is a discussion of the 9 trig sub exercises that we have. I'm going to guess that some of these down here at the bottom get a little bit more stifling, and even some of these here in 6 and 7 might get a little bit complicated, but trust in the process. Always take things in bite-sized pieces. As you get things to trig functions, think in terms of 7.2, section 7.2 logic, where, hey, if we got to use another substitution and go 2 layers deep in our substitution, so be it. Such is life, and it's a part of the process. So I wish you luck with this, and I will catch you next time.